Well, hello everyone. So we shall be studying about the next module of the syllabus, that is the basic principle of spectroscopic techniques, in which we shall be particularly dealing with actually what is required for any of the spectroscopic technique to be taken under. Now, the basic principle that underlies the spectroscopic technique actually involves the electromagnetic radiation. The use of electromagnetic radiation, we shall study in detail how the electromagnetic radiation is used, and actually different parts of electromagnetic radiations are used for different spectroscopic techniques. Now, before we move further for studying the spectroscopic techniques, let's try to understand a bit about the electromagnetic radiation. The electromagnetic radiation, as we all know, the common source of electromagnetic radiation is the sun. The radiation coming from the sun is called as electromagnetic radiation, and we all know that it can travel through vacuum also. Also, the electromagnetic radiation consists of a particle nature as well as wave nature. That means it can behave as a particle also, as well as it can show the features of a wave also. That is well studied under the quantum mechanics, which is a separate branch of chemistry, in detail. Okay, now when we say that electromagnetic radiation consists of a wave nature, what do we mean by that? We simply mean that it can move like a wave. The ripples that you can see on the surface of the pond when you throw a small piece of stone in it. So it can move like a wave. It possesses the wave nature. And when we say that it possesses a wave nature, we also mean to say that it is being associated with electric as well as the magnetic field. So such radiations that possess the electric as well as magnetic field, they are called as electromagnetic radiation. And these electric and magnetic fields actually, they are moving perpendicular to the each other. Now in this figure, you can see the propagation of wave in one direction. Now let's suppose that this propagation direction is the x-axis. So the wave is propagating along the x-axis, and the electric field is just perpendicular to that axis, denoted by the blue shaded region. So the electric field is at 90 degree to the direction of propagation. Another field that is also over there is the magnetic field, and if you keenly observe the angle between the electric field and the magnetic field, it is 90 degree. That is perpendicular to the each other, which is denoted by the pink shaded region over here. So in short, the electromagnetic radiation is any radiation which consists of electric field as well as the magnetic field, which are perpendicular to each other. Fine. This is due to the wave nature of the electromagnetic radiation, wherein we also know that the electromagnetic radiation possesses the particle nature also. Now, considering this wave nature of the electromagnetic radiation, let's try to understand the nature and the properties of electromagnetic radiation. It has a characteristic feature of a terminology that we use as frequency, denoted by mu. Now, what is frequency? Typographically, it can be defined as the number of times electric field radiation oscillating in 1 second. But if we try to understand this terminology, having a closer view at the waves, we say that, let's try to have a look at the earlier slide. Now, these waves are moving, okay? This uplifted portion is called as the crest, and the valley, it is called as the trough. Okay, so this is the crest, and the valley, it is called as the trough. Now, when we correlate the crest and the trough, to understand the terminology of frequency, we say the number of crests that pass through a particular point in 1 second. That is called as its frequency, the frequency of the wave. Okay, let's try to simplify it further. Suppose I mark any point. Now let's go back to the earlier slide. Suppose I mark any point on this particular figure. Let's say this point. Okay. So the number of crest, or let's say the number of troughs. Okay. It can be either crest or either trough. So the number of crest or the number of trough that pass through this point that I have marked in 1 second. Suppose there are 10 troughs passing through this point in 1 second, or let's say 20 crests passing, fine. So that defines the frequency of the wave. The unit of the frequency is hertz, and 1 hertz is equal to 1 cycle per second. Frequency of mu is equal to c over lambda, where c stands for the velocity of light in vacuum and lambda stands for the wavelength of light. Now, when we have mentioned the terminology of wavelength, let's try to understand what wavelength is. It is denoted by lambda, and it is actually the distance between any two nearest paths, or let's say any two nearest crest or any two nearest troughs. Okay, so the distance between any two nearest crest, or let's say in terms of any two nearest troughs of the wave which are moving in the same phase, it is called as wavelength. Fine, and it is denoted by lambda. Let's come back to the relationship between the frequency that we have understood with the wavelength. So it is c is equal to nu lambda. Fine. C is equal to mu lambda, where c stands for the velocity of light, mu stands for the frequency that we have just understood. That is the number of crest or the number of trough that pass through a particular point in 1 second. Fine. And mu times lambda. Okay. Now, this is a relationship between the wavelength and the frequency in terms of the velocity of light. The energy of the electromagnetic radiation, which carries frequency mu and a wavelength lambda, it is given by Planck, and it is called as a Planck's equation, wherein E is equal to h mu, or if we write it in terms of wavelength, it is equal to hc over lambda. Here what we observe that the energy of any electromagnetic radiation moving in a particular direction, so that energy is directly proportional to frequency of that radiation. Okay, so if the frequency of a particular radiation is more, definitely it is going to possess a higher energy, and if the frequency